So u1 u2 is equals to n1 0, n2 0, n3 0, n4 0, 0, n1 0, n2 0, n3 0, n4 times u1 at node 1, u2 at node 1, u2 sorry u1 at node 2, node 4, and u1 at sorry u2 at node 4. So if I've taken this is my node 1, node 2, node 3, node 4, I have u1 at the node 1, next u2 at node 1, u1 at node 2, u2 at node 2, u1 at node 3, u2 at node 3, u4 at node 1, sorry, u1 at node 4, and u2 at node 4. This is 1 and this is 2 direction. Okay, so this is what we have showed, and further we showed that epsilon, which is nothing but epsilon, which is epsilon 1 1, epsilon 2 2, epsilon 1 2 is equals to dou n1 by dou x 0, dou n2 by dou x 0, dou n3 by dou x 0, dou n4 by dou x 0, 0, dou n1 by dou y 0, dou n2 by dou y 0, dou n3 by dou y 0, dou n4 by dou y, and this is 1/2 dou n1 by dou y, 1/2 dou n1 by dou x, 1/2 dou n2 by dou x, sorry, 1/2 dou n2 by dou x, 1/2 dou n3 by dou y, 1/2 dou n3 by dou x, 1/2 dou n4 by dou y, 1/2 dou n4 by dou x times again u1 for the node 1, u2 for the node 1, u1 for the node 2, u2 for the node 2, u1 for the node 3, u2 for node 3, u1 for the node 4, u2 for the node 4. We simply call this one as epsilon is equals to b times t. And similarly, and we called our u as n times d. Here this n matrix is this one. So what I will do, I will replace this by u. Okay, it's just notational things, so nothing big deal about it. So I don't want to confuse you, so we'll call this as capital U. So, and this as capital U. So it is, I will call it as U dash, where U dash is given by delta V1 1 at the node 1, delta V2 the node 1, virtual displacement at the node 2 in the one direction, virtual displacement at the node 2 in the second direction, virtual displacement at node 3 in the first direction, virtual displacement at the node 3 in the second direction, virtual displacement at the node 4 in the one direction, delta virtual displacement in the second direction at node 4. This is my U dash. U is, as we this is our capital U. Okay, so now, and we invoke our principle of virtual work from the previous class, which is, let me reflect the previous class. So I will bring this thing, principle of virtual work. So this is the internal energy phase array boundary. So we have already shown the graph last time. That is, when you have a domain omega and a boundary where on gamma u, u is equals to u star is mentioned, which is kinematic boundary condition, and t is equals to t star on gamma t. So where I already shown that your gamma t is not only this, but also all these things is your gamma t, and your gamma u is, this piece of it is gamma u. So this is gamma u, and this is all gamma t, where at this place my t star is only 0. These are traction free surfaces. At this place there is some traction which is mentioned, where all other places the traction is free. So these are all also called as traction free surface, is this portion of it where there is no point loads or kind of a force acting on it. Where there is non-zero force, there is t is equals to t star. Okay, at all other places this t star is going to 0. So this guy is, you can write it as with this gamma t as this as the thing. So with this, what we'll do is we'll make use of our solution and put it here. So as we just saw, our virtual displacement is given by like this. You can also rewrite this as u dash transpose n transpose. So if your delta v is written as u dash n transpose, then your delta, which is, this is virtual displacement, this is virtual strain. This would follow the same thing, so which would be U dash transpose B transpose. Why? Because we know epsilon is equals to B into U, where U is equals to N into capital U. So by the same analogy, you can write these two in this manner. Okay, this to here is this one, and hence from this to here is the virtual strain is in this manner. So now we have this term virtual strain that goes in the first term, and then virtual displacement, then all other stuff. So let us rewrite this value as internal energy integral sigma ij delta epsilon ij, right? dV. So this can be written as, we know that sigma is equals to d times epsilon from our constitutive framework, which in for linear elasticity we have already given it. For linear elasticity, D was supposed to be given in the previous things for the plane stress and plane strain condition. So what I will write this thing to be, this can be written as right dV, which you can write this thing as this is the transpose of it times sigma dV. So if I substitute this one, this will be U dash B transpose this one will be D times epsilon dV. Further, I can break this thing into U dash transpose B transpose D is as B times U dV. So in which I can I will write this one as U dash transpose and integral B transpose D B dV into U. So where I call this thing as u dash k u. This is your internal energy. Now let us look at the external energy. For the external energy, it is dV transpose body forces work done by the body forces is into dV transpose into V integral transpose times B dV, that is equals to integral u dash transpose n transpose B dV, which I call it as u dash transpose integral and transpose V dV. So this further I call it as u dash transpose F coming from the body forces. This is integral over the domain omega. Similarly, work done by the traction or by the external traction is integral gamma delta V transpose times P dA. So that is integral dash transpose and transpose P dA this over gamma. This integral is over the surface gamma t to be specific, because there is nothing mentioned on the gamma u. So this is u dash t times F traction forces. So now I can write my principle of virtual work after numerical approximation u is equals to n times u delta v is equals to n times u dash, or delta v transpose is equals to u dash transpose n transpose. We can write it as u dash transport times k into u. This is coming from the internal energy, internal strain energy, minus coming external work done by the body forces minus tractional forces. Let's call it as pi. Now this is the total potential energy so we want the choice of u dash such that this total potential energy, the rate of change of this potential energy is 0. That is, for equilibrium dou pi by dou u dash is equals to 0. So if I take this and differentiate with respect to dou u dash, I'll get that this is capital U implies, so this gets differentiated, this is independent of u dash, so this just remains, so it is k into u minus fp minus ft equals to 0. This together I call it as minus f. Then we can write k times u is equals to f. This is our equilibrium condition in discrete or finite element sense. So that means this is same as del dot sigma plus pi equals to E is equals to 0, subjected to all the boundary conditions and other stuff. Similarly, or it is also equal to the principle of virtual work, or in the finite element sense, this is the same as this is ku is equals to f. So when somebody says that equilibrium condition in finite element sense, will directly use k is equals to f, where k is element stiffness matrix and u is degree of freedoms on the element, and this is nodal force due to body and tractional forces. So once this is we have derived, which is same as the spring or for a bar or something like this, we have come to the very similar form even here. So that means no matter in how the formulation is, we get same ku is equals to f everywhere, and the k element properties what we discussed for the bar or a beam or something, most of them will retain the same thing. Okay, this is kind of symmetric, and it is singular if you don't impose any kinematic boundary conditions and so on so forth, because we have, even when deriving, we used small strain theory. So now let us understand this problem and try understand this further and try to solve few problems. Okay, and for this we also have to look into various how to compute this k for, let's say, a quad element or for a um, triangular element and other things. And once that is done, the assembly would be very similar what we have done in the previously. Only thing is there is multitude of the dimensions. Earlier we have done for a kind of a bar and beam example with an elastic foundation. The same things holds true. The assembly will be there, kinematic boundary condition applied has to be there, KUU has to be condensed and then inverted to find the unknown degrees of freedom. Knowing the unknown degrees of freedom, the reaction forces or the unknown forces can be computed as it is. So all the things that one has learned in the 1D sense would remain. So let's only focus on development of K, looking at the definition. Okay, the definition what we have given above, K is integral of V transpose D V integral over the volume. So let us have a look at these things. Okay, so let us go back a little bit, and for example we have seen this example with minus a plus b, a comma b, a comma minus b, minus a comma b, and we said that for n1 x comma y in the previous case. Let me just quickly flash it. So a minus x. So let me just bring this as it is. So n1 x comma y is a minus x, b minus y, 4ab, and all those things. So now, before I proceed further, I need to also differentiate them with respect to x and y's. So let me also find these things. So let me put it in this manner. So dou n1 by dou x is equals to, if I differentiate it only with respect to x, so I will get minus 1 into similarly when I do dou n2 by dou x, I would get b minus y 4ab. Then if I differentiate with respect to dou n3 by dou x, I'll get b plus y by 4ab, and dn4 by dou x is equals to, I'll get it as b plus y, the minus sign 4ab. Because there is a minus sign, when I differentiate this, I'll get minus 1. Here it is plus 1, and the other things remain. Similarly, when I differentiate with respect to dou n1 by dou y, I will get minus of a minus x by 4ab. Let me have a look. So when I differentiate it with respect to y, this will give minus 1. The other things remains as it is. So similarly, dou n2 by dou y is equals to minus of a plus x by 4ab, and dou n3 by dou y is equals to a plus x divided by 4ab, and dou n4 by dou y is equals to a minus x divided by 4ab. So these are the these things that we have obtained. Since we have obtained this, now we can, I'm in a position to write b. What is b? Our definition of b is dou n1 by dou x 0, dou n1 by dou n2 by dou x 0, dou n3 by dou x 0, dou n4 by dou x 0, 0, dou n1 by dou y 0, dou n2 by dou y 0, dou n3 by dou y 0, dou n4 by dou y, and this one is 1 half dou n1 by dou y, 1 half dou n1 by dou x, 1 half dou n2 by dou y, 1 half dou n2 by dou x, 1 half dou n3 by dou y, 1 half dou n3 by dou x, 1 half dou n4 by dou y, 1 half dou n4 by dou x. So by looking at for the above given element, which is for this element, the K matrix, which if we want to do it, since we have this differentiations of the thing, I can quickly write this as the first one is minus b minus y by 4ab 0, b minus y by 4ab 0, b plus y by 4ab 0, minus b plus y by b 0. Similarly, this is 0. The next one is minus a minus x by 4ab. This is 0. This is minus a plus x by 4ab 0, a plus x by 4ab 0, and a minus x by 4ab. This one is little bit, we have to just, this would be minus a minus x by 8ab, because this term by half, this term by half, this term by half would come here. So minus b minus y by 4ab. Next is, this one is minus a plus x by 4ab. b, sorry, these are 8ab's. I'm sorry about that. This is 8ab, and this is also 8ab. By 8ab, a plus x by 8ab, b plus y by 8ab. This is a minus x by 8ab. This is b plus y, the minus sign with 8ab. So this is our B matrix. Let us develop the same thing in the MATLAB so that we can use it for our computations. So okay, let me just develop a new element. I don't remember where it happened. So our basis function. So let me develop for required. So let me give as 1a, and I'll increase the font view. Seems so our capital basis is given by 1 x y and xy is our capital basis, and our A matrix was been evaluated at this been evaluated at node 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 1, node 2, node 3, node 4. So as we did last time, minus A minus B, A star B, 1 A minus B minus A star B, so 1 A B A star B, 1 minus A plus B minus A star B. So our shape functions is equals to x star inverse of A. So let me just run this. So so I will try to simplify it so that we can understand it better. So So as we simplified it, that is the same shape functions a minus x b minus y, a plus x b minus y, a plus x b plus y, and b plus y and a minus x, which is the same thing as we have written here. These are our shape functions, right? Then what I will do is I'll call it a small n for different purposes. Then I will write my capital N is equals to n1 0, n2 0, n3 0, n4. Then this is 0, this is n1, this is 0, this is n2, this is 0, this is n3, 0, and 4. Our shape functions. Okay, so our shape functions is obtained by this. So I will call this as so as I said earlier, this is capital N. As we discussed, this is n1 0, n2 0, n3 0, n4 0 on the first row, and the second row 0, n1 0, n2 0, n3 and 0, n4 on the second row. Okay, so our n has been done. Now what I will do is I will obtain nx and y, which is like, I'll call it as dnx and dny, which is differentiation of quad for the shape functions provided n has been given. So we know that and this is given by dnx I will take it with respect to small n. We'll make it with respect to small n so that it will be much easier for us to deal with it. So dnx is equals to diff n comma with respect to n with respect to 1, and dny is equals to differentiation of n with respect to y comma 1. So what we'll do is let's also send n comma n so that we, since we are using both the thing in a different manner, so the small n we are getting dnx and dny. So let us see what is our I will also do the simplification. So Okay, so there must be some problem. So let me just check. I have doc. It is the other way around. So let me just check this one. So let me just see what is happening. Let me take this expression. Yes, I don't know, for some reason it is giving a difficulty. Let me just make it as this guy. Okay, so we are good. So it is giving back our dny and dnx as we have seen. So dnx and dny, if you look at here, let us run it. So the first term is, as we seen here, the first one is minus by by 4ab, and dny is minus a minus x by 4ab, as you can see here, and the rest of the things would also be matching. So b minus y by 4ab and minus of a plus x, and the rest of the things is matched. So I have the correct ones. So now what I'll do, I'll go back to this, and B is equals to strain displacement matrix coming from dnx and dny, right? So which can be represented as a function delete, and so our B is defined as I said, dnx 1 0 dnx 2 0 dnx 3 0 dnx 0 4 0 and the next one is 0 dn y 1 0 dn y 2 this is 0 dn y 3 0 dn y 4 0. Here it is dn y 1 by 2 dn x 1 by 2 dn y 2 by 2 dn x 2 by 2 dn y 3 by 2 dn x 2 by 2 3 by 2 dn y 4 by 2 dn x 4 by 2. Let me just check dnx1, dnx2, dnx3, dnx4, dny1, dny2, dny3, dny4. This is 1 y x y x y x y x. So this is our strain displacement matrix. If you look at it, this is our the strain displacement matrix. If I run it, I should get my strain displacement matrix. This is my strain displacement matrix available as it is. Okay, so now I have obtained the strain displacement matrix. Then I will also give my stress strain relationship. The stress strain relationship PS. PS is plane stress. So P sig. So let us try to write those things. Since we already shown it last time, function, the stress strain relationship which we have given last time was, let us have a look at it from the previous class. For the plane stress relationship, it is given by E 1 minus mu square 1 mu 0 is mu 1. This is the relationship. So let me just write it here. So given E and nu, our D matrix is equals to E divided by 1 minus mu square times 1 nu 0 nu 1 0 0 0 nu minus 1 by 2. So this is our stress strain relationship, the D matrix. So let us have a look at the D matrix. So if I run my, I have to give E and nu. So let us have our D matrix. So D matrix is this thing. I mean, it has just multiplied the before factor into it. Otherwise, what you are saying is the same as what we have plotted it. Or I can just write simply a simplification of it. So this is our so there was one mistake. This is 1 minus nu square. So let us rerun it again. This is our, so this is the D matrix where E is the Young's modulus and nu is the Poisson's ratio, and this is what we have obtained. Then what I will do is I will construct my K matrix. So knowing this, my stress strain relationship for plane stress is given by sigma 1 1 sigma 2 2 sigma 1 2 is equals to, so this is the thing. So now what we need to do is our K matrix. K matrix is given by integral of B transpose D. So let us find the multiplication of this thing. So let us call it as, so let's find uh, the multiplication of this thing and then store it in the some matrix called H. Okay, let's, so let me do that thing quickly here. So when I do that, H is equals to simplify transpose B star D star B, and this is the thing. Let us see what is my H matrix looks like. Yeah, this has given a nasty thing. Don't worry about it. We'll simplify it. We will just simplify it. So this is our B times D matrix. This is only the H matrix. I haven't solved it yet. So keep patience. We will come back to that. The purpose of choosing to solve in MATLAB is to handle this nastiness. So now our K matrix, we need to do kind of integration. So let us just look H1 comma 1. The rest of the things we are not really keen on looking at it. So let us at least have a look at the first one again. It's such a big thing. Now what we want to do is, let me just say simplify. So at most it could simplify it into this form, which is of this thing. Then what I will do is write, we don't need this, we need a symbolic integrator. So So we will use this expression, integrate the expression with the variable with respect to a to b. So we can kind of the thing. Now our K matrix is integral um, h times dv, which can be written as dv can be split as thickness into, right, per unit thickness, whatever it, into dA. That means the integral would be 0 to, so for in our case, since it is this thing, we have x from minus a to plus a, b from plus b to, I mean minus b to plus b. So I can write it as minus a to plus a, minus b to plus b, times, which is h, into some thickness times dx dy. So here we have seen that the integration with respect to x will be minus a to a, with respect to b is minus b to b. Let's take t is equals to 1. In that case it will become minus b to b, minus a to a, h dx dy. So for unit thickness, then now we know each and everything. So what we'll do is, we'll call it as hx equals to integrate h comma x from minus a to a. Let us see the command once. So it has done the integration with respect to A. Then what we'll do is our K matrix is again the same thing. Now we'll integrate with respect to y, with respect to b to minus b. So this is how you try to integrate it and kind of get the things. So our stiffness matrix can be, sorry, this is hx. Sorry about that. So we have to integrate it again. So let me put it as K matrix. So this is how your K matrix would look like. So that's what you have to integrate. When I mean I will try to show it again pictorially in this thing. So this is nothing but when you are writing it here, uh, this is h11 dx dy h12. So all the things that's to be done dx dy. So like that, entire this matrix, you know, the H matrix would be the shape of, we'll start from it. This is 4 nodes because uh, we have kind of 3 rows coming for the 3 strain variables, and then we have 4 nodes, and each node has 2 degrees of freedom. It is 3 into 8. This is 3 cross 3. Since this is 3 cross 8, the transpose of it is 8 cross 3. So the resultant of that will be 8 cross 8 for all the degrees of freedom. So this would be of 8 cross 8 with respect to the degree of freedom. This is with respect to degree of freedom 1. Okay, I'll not write with respect to, I'll write it with respect to, with the help of, this is d1, this is d2, so on up to d8, where d1 is u1 at the node 1, d2 is u1, sorry, u2 at node 1, similarly u1 at node 2, u2 at node 2, u3 at node u1 at node 3, u2 at node 3, u1 at node 4, u2 at node 4. This is d3, this is d4, this is d5, this is d6, this is d7, and this is d8. So like that you will have entries which is d1 to d8 and d1 to d8. Upon integration you will find the things. So this is how you tend to try to get your displacements. So if this one is for not for a quad but for a triangle, let us say a triangle would look like something like this. So similarly, if h is 8 cross 8, your k is also, in this case, is for the 8 cross 8. Okay, now let us come to, for triangular element with 3 nodes. Let's say node 1, node 2, and node 3 with, let's say, x1, y1, x2 y2 and x3 y3, in that case you'll see that here your basis vector capital X would be 1 x and y, and your capital A would be 1 x1 y1, 1 x2 y2, 1 x3 y3, and your shape functions n is obtained by and your capital N would be n1 0, n2 0, n3 0, 0 n1, 0 n2, 0 n3, and your displacements are given as your u1 u2 is given as n times u, where u are u1 node 1, u2 node 1, u1 node 2, u2 node 2, u1 node 3, u2 node 3, which is also known as your degree of freedom 1 through 6, d1 d2 so on, your d6. So similarly your B transpose matrix B would be nx, let me write it in that manner, so nx1, nx2, and this is ny1, ny2, ny3, and this is ny1 by 2, nx1 by 2, ny2 by 2, nx2 by 2, ny2 by 2, and x, so this is 3 by 2. So where nx is defined as dou n by dou x, and y is defined as dou n by dou y. And again your K matrix is as it is. K would be 6 cross 6. In this case it would be integral B transpose dB dx dy, where these are obtained in the above fashion and these are obtained in this, and this integral is also done as it is using some using a analytical integration as we mentioned here, and we can see that this matrix is 3 cross 6, so this is 6 cross 3, this is 3 cross 3, this is 3 cross 6, so our ultimately these two gets consumed, these two gets confused, we get 6 cross 6. So your K matrix is 6 cross 6 for corresponding to D1 to D6, and correspondingly for the rows and columns from 1 to 6 to 1 to 6 degrees of freedom. So this is how you develop your stiffness matrix for let's say a quad element or for the um, triangular element. The same procedures can be obtained, can be used for any given thing provided your basis is properly chosen. Okay, so that's the difference. Now what we'll do is the rest of the assembly setting up the boundary conditions all remains same. So what I will do is I will talk about the behavior of a constant strain in the bending, so that we will see the performance of it. So let us consider So anyway, why we call it as constant strain triangle, you need to understand here, because at most this is a function, before I tell that. So since these functions are linear in terms of x and y, so when I differentiate with respect to the thing, the strain displacement matrix would be purely in terms of uh, constant. So the b, if b is constant matrix, then what happens is automatically your strain, because strain is given as for a triangle, since you have either it is just linear in terms of x and y, there is no xy terms involved in it, unlike the unlike this quad where you have a basis vector which has x and y involved in it. for, for a quad, for this quad, we know that the, our basis vector is xy and xy, so that this linear bilinear in both the things would be giving you bilinearity. However, in this triangular element, you will not get such kind of things. You will only get linear in terms of only linear shape functions. There is no bilinear term that is involved because there is no xy term that is there. So when you differentiate it with respect to x and y, what will end up is, in here you'll get B matrix which is full of constant coefficients. That means if this B matrix is full of constant coefficient, your epsilon is also constant, and hence the triangles are also called as constant strain triangles. So let us see the behavior of the constant strain triangles in bending. So that means consider a beam, and let us see, let's have one uh, triangle. So, and such that let's say this distance is c, and this distance is also c, and uh, let us take origin here for this element, and let's say this distance is L, and this distance is also L. Okay, so that means, let me rewrite it outside. So I have a triangle which is like this with a coordinate system like that. Okay, so in that case, my uh, node 1, node 2, node 3 coordinates would be, this one is with a distance L and a distance minus C. This coordinates is with a distance X and y distance is C. This one is minus L and it's on the X axis, so y is 0. These are the nodal coordinates. Now uh, let's have this as an element. We'll come back to that. Now let's subject this bar, sorry, beam, to a pure bending. Okay, so to pure bending. When you subject it to the pure bending, from the theory of elasticity, the exact solution for this problem is from theory of elasticity. I'm not deriving this, but I'm just writing it for the convenience. The correct displacement field associated with this pure bending is given as u is equals to u bar by, and V is the y displacement. This is x displacement. Where mu bar is some coefficient. Okay, so let us use this. Since this is an exact relationship, we can also get our epsilon x, which is equals to dou u by dou x. If I do that, my epsilon x would be given as, and if I do, I will write it as epsilon xx, and epsilon yy is dou u dou v by dou y. If I do that, I'll get it as minus mu u bar by CL. And let us also do gamma x y, which is um, epsilon xy plus epsilon yx. And you will see that under the pure bending, this, if you compute these things, you will see the shear strain has to be 0. So this is the exact solution what we have got. Let's say exact solution. We haven't derived this, we are only invoking this or using this from the theory of elasticity, which you might have learned in some AMOS course. But now we are seeing, let's compare this solution with respect to the solution we are getting it from the finite element solution. So now what we do is, we will try to evaluate for our element the displacement we know that in finite element the displacement are exact. So I can say that my u1 e1, that is the displacement at node 1, is given by, if I substitute this, I can directly get the exact solution. So I'll substitute L and minus C in these things, so it should be the same. So that is at node 1, that is L and minus C. If I substitute in this thing, I'll get, this is minus u bar, and I get this as u bar CL into minus L square minus mu C square as my thing at node 2, that is at L comma C, my u2 v2. If I substitute in the above expression, in this above expression, I'll get u bar by 2cl minus L square minus, and at node 3, that is at L comma 0, my u3 and v3 is given by 0 and minus u bar by 2c into, yeah, this is obtained just by substitution. Now we know that, so that means my U matrix is nothing but this is D1, D2, this is D3, this is D4, this is D5, this is D6. My U matrix is nothing but D1, D2, so on D6. And strain is given by B times of so for the convenience I'm directly deriving it, but B you can just derive it using such a finite element program, such a MATLAB program, or you can try to do it yourself with a pen and paper, so it's not a big deal. If I compute using this expression for the B, which is obtained through the above procedure which I've shown, you will get that epsilon x, or you will get your epsilon 2b after evaluation, you will get something like this. It is 0, 0, and 1 by c minus gamma c by 4, sorry, minus mu c by 4l square to u r. Now if I compare the strain with respect to this at the same locations, you will see it is quite different. The strain, if I substitute C at, let's say I mean this is the expression for epsilon x, so I don't have to substitute it. So this is the expression for epsilon x, epsilon y. So anyway, let me write from the exact solution. My epsilon was coming to be mu bar y by CL minus mu bar by CL at 0. This is your exact solution. Now if you look at the epsilon from CST, this is quite different. So let me just copy it again for you. The exact solution says that if you compare the exact solution with respect to this, they were nowhere comparable. So that means our constant strain triangle seems to be behaving badly under the bending. But however, most of the time people try to use CST because you can create an unstructured mesh using the triangles. So, and for complex geometries, people cannot obtain a structured mesh, so most often try to mesh it with using unstructured mesh using triangles. So why people are using it? So one has to understand this procedure. Even though if you want to model a beam with a single element, it behaves badly, but if you tend to use many elements along the along the depth of the beam, what will have is you will have a constant strain represented all throughout, and it will be a better approximation. But if you use only one element along the thickness direction, it will behave badly because it will not represent it. So even though it is seemingly bad, but if you use many such kind of an elements along the thickness, it will give you better rank. So whenever people are modeling in the thickness direction, it is always advisable to use more than 3 elements so that you can represent even with the constant strain, you can represent some kind of variation across the depth of the beam. Okay, so that's the reason. Then even though this behaves badly as a single element, it is widely used with many elements to provide a decent approximation to your exact solution. Okay, at this point what I will do, I will stop and I will check if you have any questions today, and then